Good day to you all. Today we'll discuss the CPSR. As you have seen in the previous video, the current program status register is a special purpose register in the ARM architecture. It is accessible in all processor modes. It contains the condition code flags, interrupt disable bits, the current processor mode, and other status and control information. Right? Each exception mode also has a safe program status register, as we have seen in the earlier video, right? That is, it is used to preserve the value of CPSR when the associated exception mode occurs. So all in all, this CPSR it maintains, what action currently is going on in the, you know, the registers R0 to R15, right? So user mode and system mode do not have SPSR because they are not exception modes, right? All instructions which read or write the SPSR are unpredictable when executed in user mode or system mode. Please remember that. It's a small note. Okay, now let's come to the important part. Let's see this diagram. As you already know, all ARM registers are 32 bits. Please do not forget that. Right? Starting from bit number 0 to bit number 31. Bit number 0 to bit number 31. Yeah. So let's start from bit number 0 to bit number 4. These are 5 bits. Bit number 0 to bit number 4. These are specifically assigned for the type of mode, the processor mode that can be defined. So there are total of 6 processor modes. First is user and system, then fast interrupt request, supervised, abort, and undefined, right? So based on the bit combination, the processor will know, which kind of mode it wants to operate upon. Bit number 5 is assigned for thumb state. Mm, ARM CPUs can also execute thumb instructions, which are basically 16-bit long. We'll see this in the coming slide. It's explained or it is mentioned in detail, right? Then bit number 6 is for fast interrupt request. Bit number 7 is for interrupt request. Both combined together are called interrupt masks. Then starting from bit number 8 to bit number 27 are undefined. They are not used basically because there is no requirement for it. And since it's, all instructions are all registers are 32-bit long, it has to be there, so no content is given there, right? Now, the important or very important part are the last 4 bits. Those are V, C, Z, N, or in short, in the reverse order, also known as NZCV, where V defines the overflow condition, C defines a carry, Z defines 0, and defines negative. Please do not forget this. NZCV. This defines the condition flags. Right. Okay, let's see this control flags. Right. As you can see in the diagram, bit number 0 to bit number 7 are called control flags. So the control bit change when an exception arises and can be altered by software only when the processor is in a privileged mode. Right? Okay, let's see this in details one more time. Let's associate the registers, user registers that are there along with the CPSR, right? So as we know, R0 to R12 are called general purpose registers, right? R13 is reserved for programmer to use it as a stack pointer, as mentioned earlier. R14 is the link register which stores a subroutine return address. Again, this we'll see in the coming videos. Do not worry about it. I'll explain it in details in the coming videos. For now, just remember that it holds the return address of a subroutine. R15 contains the program counter. I hope that is clear. Then condition flags or condition code flags in CPSR: N for negative, Z for 0, C for carry, V for overflow. So the least significant 8 bit of the CPSR are the control bits of the system, right? The other bits are reserved, as we saw earlier. That's the same diagram is being given here again. So the use of R13 as stack pointer is a programming convention, right? Whereas use of R14 and 15 as the link register and program counter is enforced by the hardware. So R13 depends on the programming convention. It's depends upon the program, right? Right. Okay. Again, same thing has been explained here. Now, when do these flags change and when what do these flags imply? Let's see. So negative condition flag or n bit is set to 1 if the result of the last flag setting instruction was negative. That means the processing of the whatever kind of process operation you are doing, addition, subtraction, or multiplication, or whatever it is, if the result is negative, this flag will be turned to 1. That means bit number 31 will be 1, right? Similarly, Z bit, zero condition flag, set to 1 if the result of the last flag setting instruction was 0, uh, and to 0 otherwise. If it has some value, maybe positive, maybe negative, anything. If it has any value other than 0, even if it's single bit out of the register, say R0 we are considering, R0 has 32 bits. Out of all those bits, if any bit is 1, this Z flag will be 0. It will not turn to 1. The only condition that Z flag becomes 1 is when all the 32 bits of register, any register, say R0 to R12, right, general purpose register where you have stored some result is 0, then it becomes 1. Then C bit or carry condition flag is set to 1 if the last flag setting instruction resulted in a carry condition. Right? Again, we'll see this in the numericals as well. We have them. I'll show you in a while. Then V bit is for overflow condition, set to 1 if the last flag setting instruction resulted in an overflow condition where one carry was there from the bit number 31 and there is no place to store it. Right? We'll see this in the form of numericals so that it's crystal clear to you. Right. Let's see the first. Um, what is that? The control flags, right? So these bits determine the processor mode as shown in table 2.3.1, right? Bit number 0 to bit number 4. So these are all the processor modes as given here. There are 7, or user and systems are sometimes or most of the times combined together. Okay, it's either way it's correct. So all these codes you don't have to specifically remember them, but better to know, right? Abort is 10111, fast is fast interrupt request is 10001, interrupt request is 10010, and so on, right? I hope you can remember them, but if not, there's no problem. Then bit number 5, that is thumb state bit. Now, this bit gives the state of the code. The state of the code determines which instruction set is being executed, right? There are 3 instructions in total. One is ARM, one is thumb, and the other one is called Jezero. So one of the 3 instruction set is active when the processor is in ARM state, thumb state, and Jezero state respectively, right? So if you are trying to execute from thumb instruction set, then this flag or this bit is set to 1. Otherwise, 0. Right? And Jezero bit is not used right now. You don't have to worry about it. Bit number 6 and 7, there are 2 interrupts available on ARM processor, interrupt request and fast interrupt request. So these are maskable interrupts and their masking is controlled by bit 6 and 7 of CPSR. Right? Bit 6 is for fast interrupt request and bit 7 is for interrupt request. When a bit is set to binary 1, the corresponding interrupt request is masked, and when a bit is 0, the interrupt is available, right? Whenever these conditions apply. Again, interrupt requests and all. For more details, you can check out the coming videos, what they actually do. Then condition code flags, right? Bit number 28 to 31. This we have seen again, where these flags in CPSR can be tested by most instruction to determine whether the instruction is to be executed. Bit number 28, as we saw, is set to 1 of 2 ways. For an addition or subtraction, B is set to 1 if signed overflow occurred regarding the operand and result as 2's complement signed integer, or for non-addition or subtraction, B is normally left unchanged. Yeah, they do not affect it. Carry flag, bit number 29, it is set to 1 of 4 ways. For an addition including the comparison instruction, CMN or CMP, C is set to 1 if the addition produces a carry, um, that is an unsigned overflow, and to 0 otherwise. For subtraction, again, include the comparison instruction, CMP, C is set to 0 if the subtraction produced a borrow, and to 1 otherwise. For non-addition or subtraction that incorporate a shift operation, C is set to the last bit shifted out of the value by the shifter. There are shift operations as well, we will see them. And for other non-addition subtraction, C is normally left unchanged. Similarly, bit 30, 0 is set to 1 if the result of the instruction is 0 and to 0 otherwise. Then bit 31, it is set to bit 31 of the result of the instruction if the result is regarded as a 2's complement signed integer, then n equal to 1 if the result is negative, and n equal to 0 if the result is positive or 0. Please do not forget this. It will be required throughout embedded system, CPSR. Okay, now let's see how this works, right? So data, as you can see, 32-bit data is loaded from the ARM registers into the ALU. The ALU updates it in the CPSR, consistently whenever, a different processor mode arrives or exception mode arrives. And at the end, it will store the result in a register in the ARM register, right? So consistently, the status is updated, right? So in ARM, the R13, 14, and 15 and CPSR registers are called special function registers since each one is dedicated to a specific function. A given special function register is dedicated to specific functions such as status register, program counter, and stack pointer, and so on. So the function of each SFR is picked by the CPU designer at the time of design because it is used for control of the microcontroller or keeping track of specific CPU status. The R13 is set aside for stack pointer, R14 is for link register, which returns address when the CPU calls a subroutine, and R15 is the program counter. The program counter points to the address of the next instruction to be executed. The CPSR is used for keeping condition flags, among other things. In contrast to SFR, the GPR or general purpose registers do not have specific function and are used for storing general data. Right? Okay, let's see again. Now, ARM CPSR, whenever the instructions come in, the S suffix to any instruction will change the condition flag. If you give, say, ADD or add R1, R2, R3, it will simply add R2 plus R3 and store it in R1. But it will not update the condition flags. To specify that the current instruction should be able to modify the condition flags, you have to add an S to the end of the instruction, right? So most of the ARM instruction can affect the status bits of CPSR according to result. If we need an instruction to update the value of status bit in CPSR, we have to put S suffix at the end of the instruction. Okay, let's see this. All right, again, the same things are being given here, but in more details. But I think it's better if we explain this through some examples, then it will be crystal clear to you. Now let's see. Show the status of C and Z flags after the addition of this and this, right? Okay, let's see. So assume R1 equals to this 0x00000009C and R2 is 0xFFFFF64, right? Add R2, R1, R2. So ADDS. Now see, we have to do adds, right? This is not the instruction set, right? Which is to be followed. This is just to show you an example of. Now, if I add these two numbers, as you can see, if I add these two numbers, the result in 32 bits come to 0 and there is an overflow and a carry, right? What a single one is carried out, right? Now this what does it do? It makes C equal to 1 because there is a carry beyond the D31 bit, yes, and Z equal to 1 because the R2 or the result has value 0 in it after the addition. So the 32 bits that were there, right? The 32 bits, these 32 bits that are there, sorry, right? The 32 bits that were there that turned to 0 in the previous example. Okay, let's see another example. Let's say the second one, right? I try to add 0x00000009C and 0xFFFFF69, right? When I try to add them, now see this result that comes this result that comes, it's a non-zero number. In the previous example, it was 0, so Z flag was set to 1. But in this example, the result, there is some two ones are there at the end, right? And there is obviously a carry ahead. So here, can you guess what happens to the C flag and Z flag? The C flag becomes 1 and Z flag becomes 0. Yes, because from the 31st bit or bit number 31 that was here, there is a carry. And the result of the 32 bits stored in the register are non-zero. It's 5. So therefore, C equal to 1, Z equal to 0. I hope it is clear to you. Again, let's see some other examples. This is a more detailed instruction set. Previously, the instructions were not given. Let's see this. Now, show the status of Z flag during the execution of the following program. Move R2, 4, R3, 2, R4, 4. So what happens? 4 enters into R2 in the first part, 2 enters into R3 in the second part, 4 enters into R4 in the third instruction, right? Yes. So subs. Now see, there is an S at the end of the instruction. Why this S is required? Because only if you add S to the end of the instruction, then and only then will it update the condition flags NZCV. If you do not give S, it will subtract, but it will not update the condition flag. I hope it is clear to you again and again, right? So what does this do? R5 equal to R2 minus R3, right? R5 equals to 4 minus 2, as can be seen, and it is equal to 2. Same again, subs R5 equals to R2 minus R4. R2 or R5 is equal to R2 minus R4. R2 is 4 now, right? R2 was 4 and R4 is also 4. So 4 minus 4 equals to 0. Now, in the first part, when the first instruction, that is this subs, is being executed, at the time, the value of R5 is 2. Therefore, the Z flag is 0. But in the second instruction, when the second instruction arrives, value of R5 is 0. Therefore, Z flag becomes 0. Yes, I hope it's very, very clear to you, right? Hope so. If you have any questions, you can ask in the comment section. Now, let's see which instructions affect which flags. So, as can be seen from the table, first table, ANDs affect C, Z, and N. ORs affect C, Z, and N. Moves affect C, Z, and N. ADDs affect C, Z, and V. All the condition flags. Subs also affects all the condition flags. B affects no flags. B is actually for branch. We'll see them again in details in the coming videos. Do not worry, right? And on the right hand side, there are instructions that will make a condition flag jump branches based on the status of the flag bits. Now, because of this, we need to update the condition flags because if we want to jump, certain conditions have to be met. So to check those conditions, we we have the condition flags, and we have this branch instructions. BCS branch if there is a carry, BCC branch if carry cleared, and so on. We'll see this again. Don't worry. Right, let's come to the last slide. I hope this examples will clarify things to you. You can do it on your own and answer in the comment section. Find the C and Z flag bits for the following code. Assume R2 equals to this FF, 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 9F, and R1 is 00000061. So if you add them, what happens? Similarly, example 4 and example 5. Do let me know in the comment section and I'll verify them. Right? Okay, thank you for today. Please do not forget to like and subscribe. And if you have any questions or any suggestions, please do not hesitate to mention them in the comment section. Thank you. Good day.